guys, so welcome to Thursday's pre-recorded lecture for July 16th. We're going to start on example number, page 4, example number 3 of lecture notes week 14. So for this example, it's similar to the ones that we have been working on before, where we are trying to find sine of tan inverse of some value, except that the value right now is not given, it's left as a variable. So instead of working with, say, like sine of tan inverse of a third, we just have to think of that 1/3 as being u. Okay? So the first thing that we've done for these types of problems is define some angle. I'm going to define it to be theta. Theta is the angle that gets returned by tan inverse of u. And so under that definition, we have a goal of finding what sine of theta will be, because this tan inverse u is being represented by theta. Okay, so from there, what is the given information? Well, from the definition that we made here, one of the given information is that tan of theta is equal to u, which I'll go ahead and write as a u over 1. That way we have an opposite side and we have an adjacent side, because tangent is opposite over adjacent. We also know that the angle theta that gets returned by tan inverse has to be in the range of -pi/2 to pi/2. I'll go ahead and remind you why in 1 second, but essentially it boils down to that is what we restricted the domain of tangent to be in order to have a one-to-one function for tan. So here is our tan inverse, and tan inverse returns an angle that is between -pi/2 and pi/2. So hence the reason why we're writing that theta has to be in that range. And if you remember from yesterday's lecture, being in the range of -pi/2 to pi/2 means that we're considering quadrants 1 and quadrant 4. So I'll go ahead and draw a diagram that includes quadrant 1 and quadrant 4. Now notice for the numeric examples that we had been considering, whatever this number was helped us determine which of the two quadrants we would draw the diagram in. But in this case, since u is a variable and can represent any number, we're going to have to draw the diagram in both quadrants, quadrant 1 and quadrant 4. So I'll start off by drawing the diagram in quadrant 1. So in quadrant 1, if I have this being angle theta, then that would be my opposite side. This would be my adjacent. So opposite would be, actually let me draw that a little bit larger since I have the room, that way it doesn't get too cramped. Okay, that's probably a little bit better. Okay, so the opposite side is u, the adjacent side is 1. Notice that the 1 is positive, which is consistent with x being in the positive, the direction of the adjacent side being in the positive x direction. Okay, and so we said we want to be able to find sine of angle theta. So I'm going to need the hypotenuse, which means I'm going to have to use the Pythagorean theorem to help me find what that is. So using Pythagorean theorem, we'll have a 1 squared plus u squared is equal to hypotenuse squared. From there we're going to get that c squared is just going to be a 1 plus u squared. Take the square root of both sides, and technically we would have two options, plus or minus, but because the hypotenuse is always positive, we choose the positive root, 1 plus u squared. Okay, so this here becomes 1 plus u squared. And so now to find sine of theta here in this first quadrant, and actually I kind of want to make sure that I have enough room, so I'm going to go ahead and transfer this over to a sticky note and erase that so I have some room to write what sine is. Okay, so in this first quadrant, Sine will be opposite over hypotenuse. That's a definition. And we're going to have u for opposite side. Hypotenuse is the square root of 1 plus u squared. Of course, we don't want to leave it with the radical in the denominator, so we can go ahead and rationalize. And when we do, so if I multiply top and bottom by 1 plus, or square root of 1 plus u squared, in the numerator, we're going to end up with sine theta equals u times radical 1 plus u squared. And in the denominator, the squares, the square roots rather, are going to cancel out because we are going to end up with this expression squared. So we're going to get 1 plus u squared. Okay, so that's in the first quadrant. What happens in the second quadrant? Well, actually, in the second quadrant, we're going to get exactly the same thing. And what I want you to be careful about is the following. So we said tangent, if the angle is in quadrant number 4, this would be our reference angle instead. And tangent is opposite, which is u, over adjacent, which is still 1. Now, because we are going in the negative y direction, it's a common mistake to want to write a negative u here, or negative in front of the u. The reason why that would be incorrect is because u is representing any number. So just like here, it might be representing 2. Down here, it's probably representing something like a negative 2. So this expression is actually valid for both quadrants. Okay. So I'll just write that down as a note. In quadrant 4, I'll just write Q4. The same result holds. Because u is a variable representing any number, positive or negative. So just to write our final answer with the form that they gave us, which is sine of tan inverse, I'm going to write sine of tan inverse of u is equal to u times the square root of 1 plus u squared all over 1 plus u squared. And that would be our final answer. Now you can always test that this is correct by plugging in some value. The only thing that you have to make sure that you pick u so that it is in the allowable domain of tan inverse. So if you take a look at tan inverse, well, okay, here there's not too much of an issue because you can plug in whatever you want. Okay, the domain is from negative infinity to positive infinity, so we can plug in whatever. So let's just say we replace u with, say, negative 2/3, okay, or negative 2, just the way we have it here in the diagram. Okay, so if I plug in sine of tan inverse of negative 2, okay, this is a value that we're getting, negative 0.8944 with some other decimal numbers. Now if I plug it into the right-hand side of the equation, let's see if that number still matches up. So in the numerator, I would have a negative 2 times the square root of 1 plus a negative 2 squared. Okay, and then divided by, actually let me go ahead and close the numerator. Divided by, I'll group both terms in the denominator as well. So divided by 1 plus a negative 2 squared. And there it is. Both of our values are matching, which means that at least I know that that doesn't prove it in general, because we've only shown that it works with the -2. But at least, you know, we picked something at random and it worked. So it's a pretty good indication that it's going to work for any value. But of course, you can always test some more, and then hopefully that will be enough to appease our minds that we've done it correctly. Okay, similarly for B, which I'm going to continue on a separate sheet, we want to start off by defining an angle theta for the inverse function, or part of the expression that has the inverse function. So let me just go ahead and label my sheet here. This is example 3, part B from week 14. We have cosine of 2 times arc sine of u, and I'll be defining theta as the angle returned by arc sine of u. Okay, so now we have a new goal. That goal is to find cosine of 2 times theta. And I am going to, you know, we do have those double angle formulas to help us. The tricky part here is going to be which one do we use, because there are 3 versions of double angle formula for cosine 2 theta, right? There's the 2 cosine squared theta minus 1, the 1 minus 2 sine squared theta, and the cosine squared minus sine squared. So either one that you pick should still work, but one of them is going to make our lives so much easier. Specifically, before I even pick which one I'm going to work for in the goal, let's take a look at the given. Okay. Under this definition, theta is equal to arc sine of u. Remember, that just simply means it's equal to sine inverse of u. So one piece of given information is that sine of theta is equal to u. Okay, so that actually gives me a pretty good insight as to which of these 3 I should pick. Since I already have what sine of theta is going to be, I'm simply going to pick this 1 minus 2 sine squared theta for the double angle formula. Oops, that should be sine. Reason being is that at that point, I don't even need to draw a diagram, right? I can just replace what sine theta is directly into here. Okay, so let's go in and give it a try. I have cosine of 2 theta is equal to 1 minus 2 times sine of theta, and that term has to be squared. Now I know that sine of theta is u, so I'm just going to have 1 minus 2 u squared. And that's pretty much it. Then I have cosine. I'm going to just write it with the original arguments. So cosine of 2 times arc sine of u is equal to 1 minus 2u squared. So that one worked out pretty nicely without the diagram. Okay, and again, one thing I want to point out is the fact that since u is representing any number, technically here this arc cosine would be representing an angle that is between -pi/2 to pi/2, so that means 2 different quadrants, quadrant 1 or quadrant 4. But in this case, since u is any number, it can represent either one of those options. We don't have to worry about picking a quadrant there. Okay. And so now we're going to delve into a related topic, but it's solving basic equations, which up to now we haven't really done. We've done more of an evaluation of sine inverse, cosine inverse, tangent inverse. But for these, we're going to be solving equations. And so in order to solve the trigonometric equations, I want us to get warmed up with by solving some of these algebraic equations which don't have any trig function involved. Okay. So if I wanted to solve for y here, well, simply subtract the 1 from both sides, and I would end up with 2y equals -1. Then I could divide by 2 both sides, and then my final result would be y equals -1/2. If I want to check that my solution is correct, I would simply take that result and plug it back into the equation. So if we do 2 times -1/2 plus 1, we would want to check whether or not it gives us a 0. So 2 times -1/2 is -1 plus 1. Does that equal 0? Well, yes, -1 plus 1 is 0, so that checks out. It's a true statement. That means that our answer here is correct. All right. For B, this is a quadratic equation. It's no longer linear, so we can't exactly, isolate the variable because it's present in both of these terms. So instead, there are a couple ways that you can approach this problem. When I've taught some algebra courses, I've told students, well, use the X method. And in the X method, you're looking for two numbers that are going to multiply to this last constant term. So they need to multiply to -2. And then they need to add up to the middle coefficient, or the coefficient of y. And the coefficient of y is 1. So two numbers that will multiply to -2 and add up to 1 would be a +2 and a -1, right? 2 times -1 gives us -2. 2 plus -1 gives me just 1. It's the same thing as subtracting the numbers. 2 minus 1 gives us 1. So then I can go ahead and factor this into a y plus 2 times a y minus 1 is equal to 0. So what you do for these problems is you factor them, and then we'll discuss what to do next. But it's always a good idea to kind of redistribute back these terms to see if it gives you this original expression. So not necessarily here in the work, but maybe just in your head. So y times y is y squared, and this is going to give us a -y plus a 2y. So -y plus 2y is just y. And then 2 times -1 gives us -2. Okay, so that looks good. We factored out correctly. Okay, then from there, we would set y plus 2 equals 0 or y minus 1 equals 0. The reason why is because this is saying if you take these two numbers and you multiply them together, it gives you 0. The only way that the product of two numbers can be 0 is if at least one of them is 0, right? So at least the y plus 2 is 0 or the y minus 1 is 0, or maybe both are 0. But this is now a very simple linear equation that I can subtract 2 from both sides to get y is equal to -2, or I can add 1 to both sides in this second equation to get y is equal to 1. So for these, you would have to plug it back in to check. Because of time, I won't be checking them, but you can go ahead and do so by checking those in, by plugging those in. Okay, but those would be our answers. Okay. What about for C? Well, for C, it's a little bit more interesting because we have two variables, and in one on the left-hand side, it's the product of the two. So let me just tell you what you cannot do first, okay? You cannot divide both sides by x, and I'll tell you why. Because you don't know if x is 0 or not. And if x can represent 0, then division by 0 is not allowed. Okay? Instead, we have to think of something else. So instead, what I'm going to do is I'm going to subtract an x from both sides of the equation here to have all terms on the left-hand side. And that would give me xy minus x is equal to 0. And I'll go ahead and draw a separating line here. All right, then these two terms both share x in common, which means I can factor it out. And it would leave me with y minus 1 in parentheses. And you can check that this is correct by distributing back in. X times y gives us xy, x times negative 1 gives us x. And again, we apply that same idea as before. If you take the product of these two terms and it gives you 0, that's because either x is 0 or y minus 1 is 0. And if y minus 1 is 0, that is a nice simple equation we can solve by adding a 1 to both sides, and that gives us y is equal to 1. Okay, so our answers here would be x is equal to 0 or y is equal to 1 would make the equation true. Now this one's a little shorter that I am able to check, and I want to check it because there's two answers that you have to check. So first I'm going to check x is equal to 0. If we have 0 times y, does that equal 0? Well, yeah, 0 always equals itself, so that looks good. Next, I'll go ahead and check y equals 1. If I have x times 1, does that equal x? Well, yes, because x does equal itself, so that looks good too. So those solutions are correct. Okay, so let's apply that to these equations now. They're asking us to solve each equation over the given interval. When they say over the given interval, they mean, this is what they mean. So they wrote here 2 sine theta plus 1, or they give it like this in the textbook, 2 sine theta plus 1 equals 0 over 0 degrees to 360. What they mean is theta is in the range 0 degrees to 360. Okay. It's always just going to be the angle is in that range. That's what they mean by over. Okay, so the way we're going to approach this is the same way that we approached this first equation in the warm-up. Okay, notice if y is representing sine of theta, then this equation, these two equations are identical, right? If we were to replace sine of theta with y, we would have the same equation. And so what did we do first? Well, we subtracted 1 to get 2 sine theta is equal to to negative 1. And then we divided by 2 both sides to get sine theta is equal to negative 1/2. Okay. And so at that point, this is where we have to continue one step further beyond the algebraic expression, right? Because in the algebraic expression, once we got to y equals negative 1/2, we were done. But here we're solving for theta. So in order to solve for theta, we would then take the, we would then think about the unit circle and where the unit circle in the, 0 to 360 is sine theta equal to negative 1/2. Well, first of all, let's boil down the, let's narrow down the quadrants. If sine is negative, that means that it has to be either in quadrant 3 or quadrant 4, because that's when we go down into the negative y direction. And sine is always the y coordinate of these points, right? So we're going to be focusing on quadrants 3 and 4. And it's sine theta equals negative 1/2. So I'm looking for the y values of negative 1/2, one of which is here at 210, and the other one which is here at 330. Okay, so this tells me that theta can be 210 or it can be 330. Okay. And if you want to check whether that is correct or not, well, actually let me write here, or theta equals 330. then you would do so just by plugging in. Okay, so if we check, let's start by checking this. Theta equals 210. 2 times sine of 210 degrees plus 1, will that be equal to 0? Well, let's see. Sine of 210 degrees according to the unit circle is negative 1/2. So this is 2 times negative 1/2 plus 1. Does that equal 0? This is going to be a negative 1 plus 1. Does that equal 0? Yes, that is correct. Okay, so our 210 looks good. Okay, then for theta being 330, plug it in. So we'll have 2 times sine of 330 degrees and then plus 1. Is it true that that equals 0? Well, again, sine of 330 is negative 1/2. So we're going to get exactly the same work, right? 2 times negative 1/2 plus 1, does that equal 0? Negative 1 plus 1, does that equal 0? 0 equals 0, so that's fine. Okay. Now, part B of this problem is asking us to find all of the solutions of the equation, meaning not only the ones that are in one cycle, but basically any angle that's coterminal to the solution angle. So to find all solutions, we would just take the 210 and then say in all angles that are coterminal to it by adding a multiple of 360. Same thing with 330. Any angle that is coterminal to 330 will have the form 330 plus 360n, where n can be any integer, right? Where n could be 0, plus or minus 1, plus or minus 2, any integer. Those would be all the solutions. All right, what about this part C? Part C, we have sine times tangent equals sine. And again, they want us to find all of the angles in the, for theta in the interval 0 to 360. Okay, well, that one looks, if you go back to the warm-up that we did, if you take a look at part C of the warm-up, that one kind of looks like this x times y equals x, where sine is x, tangent is y, right? And then here's sine again with x. And what did we do in that case? In that case, the first thing that we did was we subtracted x from both sides so that we had both terms on the left-hand side. So I'm going to do that here. I'm going to subtract away the sine theta. And if we do that, we'll end up with a sine theta times tangent theta minus a sine theta is equal to 0, because here these are going to cancel out. Okay, and then what did we do after that? Well, after that we said, well, x is present in both terms, so let's factor it out. And this is multiplication. So let's factor it out. So that's what I'm going to do here. I see that sine times tangent minus sine theta, these two terms share in common a sine. So I'm going to factor it out. Okay, so take out sine theta, and you're left with tangent theta minus 1 is equal to 0. So then there are two possibilities. If you multiply these two together and it gives you 0, that means that either sine theta equals 0 or tangent theta minus 1 equals 0. Okay, so now we go to the unit circle again. On the interval 0 to 360, including the 0 but excluding the 360, where is sine of theta 0? Well, let's see. Sine of theta, remember this is the y, sine of theta is 0 at 0 and at 180 degrees. All right, so theta here would be 0 degrees or 180. Over here, solving this equation for tangent, we would add a 1 to both sides to try and find all of the angles for which tangent theta is equal to 1. Again, we can try and narrow it down. Tangent theta is positive in quadrants 1 and 4. So in quadrant 1, the place where tangent is 1 is the place where sine will equal to cosine. So that's pi over 4 or 45 degrees, because if you take radical 2 over 2 and divide it by itself, it's just going to be 1. So 45 would be one of the angles. Okay, the other place where tangent is positive, we said, is in quadrant 3, so down here. And in this place, the point at which sine is equal to cosine is at 225 degrees. So if you take negative radical 2 over 2 and divide it by itself, then it's going to be 1. Okay, so tangent of 225 degrees would also give us 1. And so the final answer is that theta can be 0, it could be 45, it could be 180, or it could be 225. I'm simply listing them in increasing order. Now those are quite a few to check. I don't think they're all going to fit here in the same page, so I'm just going to do it on a sticky note. Okay, let's go ahead and check. Is it true that sine of 0 degrees times tangent of 0 degrees is equal to sine of 0 degrees? Well, sine of 0 degrees is 0. Tangent of 0 degrees is also 0 because it's 0 over 1. Does that equal 0? Oh yeah, 0 equals 0. Let's check. Next one would be 45. Is it true that sine of 45 degrees times tangent of 45 degrees is equal to sine of 45 degrees? Question mark? Well, let's see. Sine of 45 degrees, okay, here's 45. Sine would be the y coordinate, so we would have radical 2 over 2 times tangent of 45 degrees, that would be sine over cosine. So radical 2 over 2 divided by itself. So that's a 1. Is it true that that equals sine 45, we just said, was radical 2 over 2? So is radical 2 over 2 equal to radical 2 over 2? Yes, it is. So that means our 45 degree is correct. Okay. So you just keep plugging in. I won't do these last two because it's pretty much the same work. But just plug those in and you'll see that they satisfy the equation. Okay, part D now. Part D has this equation, tan squared plus tan x minus 2 is equal to 0 over the interval 0 to 2 pi. So that means that theta has to be in that range, 0 to 2 pi. Actually, let me just move this line from the previous problem a little higher. That way it doesn't look, it's not difficult to see this problem. Okay, there, that's better. Okay, so what does this look like? Again, go back to the warm-up. Go to part B of the warm-up. If y were representing tangent, it would say y squared plus y minus 2 equals 0. Okay. So this is going to factor the same way that y squared plus y minus 2 factors. In fact, let me go ahead and say just let y be equal to tangent x, and then you have y squared plus y minus 2 equals 0. And then this factors into y plus 2 times y minus 1 equals 0, which means that either y plus 2 is 0 or y minus 1 is 0. And now this is where we can bring back what y is representing. It's representing tangent. Right, so tangent of x plus 2 is equal to 0, or tangent of x minus 1 is equal to 0. So in this one here, I would have to subtract the 2 from both sides to get tangent of x is equal to -2. In the second equation, I would add a 1 to both sides to get tangent of x is equal to 1. Unfortunately for this one, this -2 is not on the unit circle, so I'm going to have to go in and use the calculator to solve. So let me just do that here on the, continue the work over here on the side. Okay. So we would get x is equal to tan inverse of 2, and this is going to be the reference angle. Remember, when we're working on the calculator, we want to go in and first find the reference angle first. Okay, so we have to be working in radians, so just make sure that your calculator is in radian mode. Okay, so then tangent inverse of 2 is giving me a reference angle of approximately 1 point. Actually, you know what? Let's leave it like this. That way we have an exact form. Okay, so the reference angle is tan inverse of 2. And then since the original value is negative, that means that the angle x has to terminate in either quadrants 2 or quadrant 4, because that is where we have negative tan. Okay, so let me just write it here. So x is in quadrant 2 or quadrant 4 because tangent x is negative. Okay. All right, so in quadrant number 2, in order to get an angle from the reference angle, remember we would have to do 180 minus the reference angle, or in radians it would be pi minus the reference angle. So that's going to be a pi minus tan inverse of 2. So now we can punch it into the calculator. I just wanted us to have a more exact form. That's why I kind of scratched out having calculated tan inverse of 2 by itself first. Okay, so pi minus tan inverse of 2 is going to be approximately 2.0344. Let's make it to 4 decimal places. So approximately 2.0344. In quadrant number 4, because that's the other place where we said tangent is going to be negative, we're going to have the actual angle. To get the actual angle in there, we would have to do 2 pi minus the reference angle. So that's going to be a 2 pi minus tan inverse of 2. Okay, so just going to insert a 2 there. We get approximately 5.1760. Okay, so that would be from this first equation. So from this first equation, we get these two answers. From the second equation, okay, which is this one over here, the tan x is equal to 1. Well, for that, I can use a unit circle because 1 is a value that we can find on the unit circle for tan. Tan being positive 1 would happen here at pi over 4, and it would happen at 5 pi over 4, so at 45 and 225, that's the same for other problems. Okay, so we would have x, or here, let me write the equation. Actually, there's enough room here. Let me write it as x is equal to pi over 4, and x is equal to 5 pi over 4. Those two would be the angles that would satisfy. Okay. So again, I encourage you to go in and check these. Make sure that they make the equation true. Go ahead and erase this. Now we're going to continue on to page 6. So for part E, we have to solve 2 sine of x over 2 equals 1 for all solutions. Okay. What makes this equation tricky is the fact that the argument is not a single variable. It's actually this expression x over 2. So for now, what I'm going to do is I'm going to let theta equal x over 2 so that I can focus on just isolating the trigonometric function. Okay. So if I let theta be x over 2, then that means that I'm solving 2 sine theta equals 1. Now, in order to isolate the sine theta, I would simply need to divide both sides by 2. And I'd have sine theta is equal to 1/2. Okay. Now I need to look on the unit circle first. What are all the angle values for which sine theta is 1/2? And they don't tell us whether they want this in radians or degrees. Let's work with degrees for now. Okay, so sine is positive in quadrant 1 and 2. So I'm going to look for quadrants 1 and 2 where my y coordinate is a positive 1/2. So first one happens at 30 degrees. Second one happens at 150. Okay. So we can say that theta is equal to 30 degrees, or theta is equal to 150 degrees. Now, because it says all solutions, we know that any angle that is coterminal to that will satisfy the same expression, 2 sine theta equals 1. So I'm going to go ahead and write the plus 360n, okay, where n is any integer, 0, plus minus 1, plus minus 2, so on and so forth. Okay. However, we weren't working originally with theta. We were working with x. So now we have to go in and replace theta with x over 2. So if I replace into this first equation, I'm going to get x over 2 is equal to 30 degrees plus 360 degrees times n. And then in order to isolate the x, I would have to multiply by 2 both sides. Okay. So multiplying by 2, these are going to cancel. And we're going to get x is equal to, distribute the 2, 2 times 30 will give us 60 degrees, plus 2 times 360 will give us 720, and then times n. Okay, so that would be part of the answer, one part of the answer. From the second equation, one that says theta is equal to 150 degrees plus 360, again, we're going to replace back x over 2 for theta. And what we're going to do at that point is, again, multiply both sides by 2. So here, these are going to cancel, and we're going to get x is equal to 2 times 150 is 300. 360 times 2 is 720. All right, for example number 5, since the work is a little bit longer, I'll go ahead and write those on a separate sheet. So for part A, we have cosine of 2x is equal to cosine x over 0 to 2 pi. Now, because the directions explicitly say use trigonometric identities to help you solve the equation. But even if they didn't give us that guideline, we would want to immediately refer to the trigonometric identities because an equation needs to be in terms of the same argument. And currently as it is, it doesn't have the same argument. This one has an argument of 2x, this one has an argument of x. So we need to make sure that the equation we are trying to solve has the same trig function with the same input. Okay? So this cosine 2x looks like a double angle formula. In fact, I have these three options for what I can replace it by. I'm going to go ahead and replace it by this 2 cosine squared, in our case x minus 1, because I want to have the same trig function at all times, just to make it simple for myself. So I'm going to replace it with 2 cosine squared x minus 1 is equal to cosine x. And this is still for x being in the range of 0 to 2 pi. So I'm just going to write that explicitly for x being in the range of 0 to 2 pi. Okay. So what would we do if this were an algebraic expression? Okay, so let me just write what I mean by that on a separate sticky. If at this point the equation looks intimidating, it's always a good idea to just write the equivalent algebraic expression. And you can do that by letting y represent the trig function. So I'm going to let y represent cosine x. In that case, we would have a 2y squared minus 1 is equal to y. And how would I solve this? Well, it has a quadratic term. So whenever I have a quadratic term, I want to have all of the terms on one side of the equation. So I'll subtract the y to get 2y squared minus y minus 1 is equal to 0. And then from there, we would try to factor the quadratic expression. So what two numbers multiply to the constant term, which is negative, actually the constant term times the coefficient of the quadratic term, because in this case, y squared is being multiplied by that too. So in this method, we're going to have to write it as 4 terms and then factor by grouping. Okay, so it's always a shortcut to look for what multiplies to 2 times negative 1, which is negative 2, and adds up to the coefficient of y, which is negative 1. Now negative 2 and 1 would satisfy those conditions because negative 2 times 1 gives us negative 2, and then negative 2 plus 1 gives us negative 1. And that would tell us that 2y squared minus 2y plus y minus 1 is equal to 0. And then I would group the first 2 terms, group the last 2 terms, see what is the greatest common factor of the first 2, which is 2y. And when you factor it out, it leaves you with the y minus 1. So essentially, you're dividing this by 2y and this by 2y. In the second group, the greatest common factor between a y and 1 is simply just a 1. So we would add or have plus 1 times y minus 1 is equal to 0. At this point, I see that the y minus 1 is present in both terms, so I can factor it out. And when I factor out this y minus 1, I end up with the 2y plus 1 is equal to 0. So if you haven't solved quadratic equations in a while, I would encourage you to go back and practice some similar problems. You can find some, I believe the textbook has some. I'll go ahead and list those out and post them on Canvas if I can find them. If not, maybe I can give you guys an extra worksheet where you can practice solving quadratic equations. Okay. But at this point, we apply that same idea as before, that if you multiply 2 things together and it gives you 0, it forces at least one of them to be 0. So either y minus 1 will be 0 or 2y plus 1 is 0. And then in that case, we would have that y is equal to 1 because we're adding 1 to both sides. Or if I subtract 1 and then divide by 2, I get that y is equal to negative 1/2. Okay, so going back to the trigonometric function then, the trigonometric equation. This is following the same order of steps. I would subtract the cosine. So I'd get 2 cosine squared x minus cosine x minus 1 equals 0. I would try to factor out this trigonometric equation. I'm just going to go straight to this result since we've already worked through it. I know that y is representing cosine, so this is going to factor into a cosine x minus 1 times a 2 times cosine x plus 1 is equal to 0. And remember, we can always try to verify simply by distributing back. So cosine times 2 cosine would give us a 2 cosine squared. Cosine times 1 would just be cosine. Negative 2 times cosine would be negative 2 cosine. So negative 2 cosine plus 1 cosine gives us a negative cosine. Negative 1 times positive 1 gives us negative 1. Okay, so that works out well. Okay, from here, multiply two things together gives you 0. That means that at least one has to be 0. So we get cosine x minus 1 is 0. 2 cosine x plus 1 is 0. Essentially, we're just kind of repeating this work. So in the end, I'll have cosine x is 1. Cosine x is negative 1/2. And so from there, I can see where cosine is going to be 1 in the range 0 to 2 pi. So cosine is 1. Let's see, where's my unit circle go? Cosine is 1 when we have 0 degrees or 0 radians. So that would be one possibility. Okay, this one would give us x is equal to 0 radians. And then the other place where it's 1 would be at 360 or 2 pi, but that's not part of the range, right? The 2 pi is excluded. So x is equal to 0 would be the only answer for that equation. For the second equation, we have cosine x is equal to negative 1/2. So we want to find all the places in the unit circle with a cosine value of negative 1/2. So that's going to happen in quadrants 3 and 2, because that's where cosine is negative. So going in quadrant 2, would see that cosine being negative 1/2 happens at 120, which is the same as 2 pi over 3. It also happens at 4 pi over 3, which is negative 1/2 for cosine as well. So it's those three solutions. And if you want to check them again, you can go in and plug them back in to the original equation, which is this one up here. Actually, maybe we can check 0 and one of these two, and I'll let you guys check the rest. It's pretty short original equation. So if I check x is equal to 0, is it true that cosine 2 times 0 is equal to cosine of 0? Question mark. Well, 2 times 0 is 0. So cosine of 0, I mean, at that point I could pretty much stop, but just to simplify the cosine of 0, we are going to get that 1 is equal to 1. So that works out. If I want to check that x is equal to 2 pi over 3 is also a solution, then I would plug it in. Is it true that cosine of 2 times 2 pi over 3 is equal to cosine of 2 pi over 3? Question mark. Well, here we're going to get cosine. This is like a 2 over 1. So it'll be cosine of 4 pi over 3. Is it true that that equals a cosine of 2 pi over 3? Well, let's see. Cosine of 4 pi over 3 is negative 1/2. Cosine of 2 pi over 3 is also negative 1/2. So that checks out as well. So in a similar way, you can go in and check 4 pi over 3. I won't do it, it's the same work, but you can go in and give it a try. Okay, part B. Part B for example 5 is asking us to find, to solve rather, 4 sine theta times cosine theta is equal to square root of 3 over the interval 0 to 360. Okay. All right, so let's see. If I want to solve, if I want to apply an identity, this looks, if I write this as 2 times 2 sine theta cosine theta is equal to radical 3, this 2 sine theta cosine theta looks just like double angle formula for sine. Okay, sine 2 theta is 2 times sine theta cosine theta. So I'm going to replace that by sine of 2 theta is equal to the square root of 3. Okay? And so I can go in and replace 2 theta, the argument, with a single variable just to make my problem a little easier for myself. I can let, for example, a be equal to 2 theta, and I'd get 2 times sine of a is equal to radical 3. And now I have a new problem, okay, or a new equation. This new equation is 2 sine a is equal to radical 3, but on top of that, originally theta, we wanted it to be between 0 degrees and 360 degrees. Okay. That means that for a, if I multiply both, or rather all 3 parts of the inequality by 2, that means that I have 0, or 2 times 0 degrees is less than or equal to 2 theta is less than 2 times 360, which means that a has to be between 0 degrees and 720 degrees. Okay, so that's my new equation, or my new problem. Okay. So how do I solve that? Well, I simply divide by 2 both sides to get sine of a is equal to square root of 3 over 2. Now, where is sine of a square root of 3 over 2? Again, look at your unit circle. That needs to happen quadrant 1 and quadrant 2 because that's where sine is positive. Sine would be looking at the y-coordinate. So first happens at 60 degrees. The other one happens at 120. That's when we have sine being radical 3 over 2. So it would happen when a is, well, actually, let me continue here. When a is 60 degrees, or when a is 120 degrees. Now, because we have a new restriction for a, it's everything 0 to 720. I have to include the first coterminal angle with, by adding 360 to 60 and 120. So it would also be for a equals 60 degrees plus 360, because that's going to give me 420, which is still allowed. Or a is equal to, let me just write here, or a is equal to 120 degrees plus 360, which is going to give us 480 degrees. Okay, but our original problem was not in terms of A. It was in terms of theta. So for each of these answers that we got, which are 4 of them, we have to replace what A is representing, which is this 2 theta. Okay, so I kind of want to rewrite this vertically. That way I can write the answer for theta right next to it. So let me just do that real quick. So we said A was 120, then there was also the angle that's coterminal to 60, which was 420, and the angle coterminal to 120, which was 480. Okay, so for these, for A being 60, I'm going to replace what A is representing. It is this 2 theta. So 2 theta has to be equal to 60, which means that theta would be 30 degrees. That's one angle. For the next one, we would have 2 theta equals 120, which means that theta would be equal to 60. For the next one, we have 2 theta equal to 420, which means that theta would be 210. And last one, 2 theta equals 480. That means that theta is equal to 240. Notice all of these angles are within the range 0 to 360. Okay, I'm going to check these just quickly using my calculator so we don't have to spend too much time. Make sure that you are in degree mode if you're following along. So I'll have a 4 times a sine of, the first angle that I'm going to check is 30. Okay, so sine of 30 times cosine of 30. That's going to give me a 1.73 with some other decimal numbers. Is it true that that equals square root of 3? Yep, same number. Then we're going to change that to 60. Same number. Then we're going to change that to 210. Okay, same number. Last one, change it to 240. Same number. Okay, awesome. So that is example 5. Well, example 5, parts A and B. Let's take a look at part C. Okay, so for part C, we have tangent of x plus radical 3 is equal to secant x, and we want to find all answers over the range 0 to 2 pi. Again, I'm going to use a separate sheet just in case I run out of room. So example 5, part C, and this is for week 14. Okay. Now, as a tip, when you're solving these equations, most of the time you want to write it with just one trig function. Here I have 2. Okay. In order to make it be, or in order to have the same trig function, I need to look at the identities and see what's the identity that would best help me in this case. So I'm going to look for what relates tangent to secant. Okay. And let's see, tangent is tangent to cotangent. There's one here with the Pythagorean identities. except that I have tangent squared and secant squared as opposed to tangent. Now, there really is nothing else that can help us with this, so I'm going to be relying on that Pythagorean identity. In order to have it apply, I'm going to square both sides of this equation, but I'm just going to be careful to check all of my solutions at the end to make sure that they truly satisfy the original equation. Because when you square an equation, it is possible that you introduce some fake answers, basically. Okay, some solutions that are not truly the correct answer. Okay, so let's go ahead and square then. I have 10x plus radical 3 squared will be equal to secant x squared. We're gonna have to distribute this, so let me write it out as the product of tan x plus radical 3 times tan x plus radical 3 is equal to secant squared x. Let's distribute. Tangent times tangent will give me a tangent squared x. Tangent times radical 3 will give me radical 3 times tan x. Radical 3 times tan x, that's the same thing, so I'm just going to add a 2 here. And then radical 3 times radical 3, that's just going to become a radical 3 squared, which is a 3, is equal to secant squared x. Okay, so now that I have the secant squared and the tangent squared, what I'll do is I'll replace the secant squared with what the Pythagorean identity says. Secant squared is tan squared plus 1. So this will become tan squared x plus 2 radical 3 tan x plus 3 is equal to tan squared x plus 1. Okay. Now I can go ahead and subtract tan squared x from both sides. And notice what happens. Here they cancel, but they also cancel here, which is nice. I have no more quadratic terms. Instead, I'm left with 2 radical 3 tan x plus 3 is equal to 1. And this one that gets left over. I can subtract the 3 from both sides. And we get 2 radical 3 tan x is equal to a negative 2. We can divide by this 2 radical 3 both sides. These cancel, and we end up with tangent of x is equal to negative 1 over radical 3. Okay. So in order to see where this happens, where is tangent of x negative 1 over radical 3, we would look at the unit circle. Tan is negative in quadrants 2 and 4. Okay, so let's see, in 2 and 4, okay, we're focusing here and here. The numbers that involve a radical 3 would be this 11 pi over 6, and they do say in radians, so 11 pi over 6, as well as a 5 pi over 3, a 2 pi over 3, and a 5 pi over 6. So those 4 are candidates. Let me go ahead and double check which one actually works. So like if we try tan of 11 pi over 6, that is going to be sine over cosine. So it would be negative 1/2 over radical 3 over 2. Okay, so that is the same thing as negative 1/2 times 2 over radical 3. These would cancel, and we'd end up with this negative 1 over radical 3. Okay, so 11 pi over 6 works. Okay, so x is equal to 11 pi over 6 is one answer. Tan of Let me see which one corresponds to 11 pi over 6 in the second quadrant. It would be this 5 pi over 6. So let's try that one out. Tan of 5 pi over 6 would be 1/2 for that sign. 1/2 over negative radical 3 over 2. So that's a 1/2 times negative radical, well, actually I'm going to have to flip if I'm dividing, so times a negative 2 over radical 3. These cancel, and I end up with a negative 1 over radical 3. So that would be my other answer. Oh, sorry, wrong. 5 pi over 6. Now you can check the other two values, but you'll see that they won't give you negative 1 over radical 3. They'll actually give you a radical 3. So far, the answers that we're getting are 11 pi over 6 and 5 pi over 6. But I still need to go and check them by plugging them into the original equation. So let's check this x is equal to 11 pi over 6. Is it true that tangent of 11 pi over 6 plus radical 3 is equal to secant of 11 pi over 6? Well, let's see. I'm going to use my calculator because I think that's going to be a bit quicker. Make sure that you are in radian mode now. So I have tangent 11 pi over 6 plus radical 3. That's giving me that number. Okay, now secant, I don't have a secant key, so I'll have to write it as 1 over cosine of 11 pi over 6. Same number. Okay, so far that looks good. Okay, the other value that we're checking is x is equal to 5 pi over 6. Okay, so is it true that tangent of 5 pi over 6 plus radical 3 is equal to secant of 5 pi over 6? Well, let's see. Gonna have same expression, but replace the 11 with 5. And so that we're getting that answer, and the secant would be 1 over cosine of 5 pi over 6. And let's see, it looks like, I'm getting a negative, so maybe I'm going to have to go back and double check that answer. Let's see. So at 5 pi over 6, at 5 pi over 6, my tangent is this 1/2 over over negative radical 3 over 2. So that's what we did here. We have a 1/2, flip the denominator, and we do get that negative radical 3. Okay, remember what I had mentioned about introducing false solutions because we squared? That's actually going to be the case here. Okay, so in this part, they don't equal each other because this gives us positive 1.1547 with some other numbers, and that does not equal the negative 1.1547 with some other numbers. So the x equals 5 pi over 6 does not work out. The only solution that we have is this 11 pi over 6. Okay. All right, so let's move on to the next example, which is part D. Okay, part D again is involving tangent and secant together. So we're going to end up squaring, which could potentially introduce some false solutions. Okay, so this is example 5, part D of week 14. And 3x plus secant of 3x is equal to 2 for x being in the range of 0 to 2 pi. Okay, so what I'm going to go ahead and do is, again, replace this argument of 3x by a different variable. I'm going to let a be equal to 3x. So I'm going to be creating a new problem. This new problem has, or a new equation, I should say. This new equation has tangent of a plus secant of a is equal to 2. But if x was supposed to be between 0 and 2 pi, including the 0 but excluding the 2 pi, now that we have this 3x for the argument, it would be 0 is less than or equal to 3x is less than 6 pi. So that means that a has to be in the range of 0 to 6 pi. Okay, we have to keep that in mind. Okay, so how do we solve this equation? Well, I want to end up with a tan squared and a secant squared so that I'm able to use the identities similar to the problem that we just worked on. So what I'm going to do is I'm first going to isolate the tangent. Okay, so we're going to have tangent A is equal to 2 minus secant A. So that way when we square, we only end up with tan squared and something involving secant squared rather than something that's going to have to multiply tan and secant together. Okay. So we're going to square both sides now. Is 2 minus secant A squared. And that is going to be 2 minus secant A times 2 minus secant A. 2 times 2 is 4. 2 times negative secant gives me a negative 2 secant A. Same thing's going to happen here, so I'll end up with a negative 4 secant A plus secant squared A. Okay, so now that we have it in this form, since this has secant and this has secant squared, when I'm using the Pythagorean identity, I'll go ahead and replace tangent with some expression involving secant. So I'll have to manipulate the identity a little bit to isolate for the tangent. This is going to give me that tangent squared theta is equal to a secant squared theta minus a 1, okay, because I'm subtracting 1 from both sides. So this tangent squared A is going to become a secant squared A minus 1 is equal to 4 minus 4 secant A plus secant squared A. Okay, so this is nice because now if I try to subtract away this quadratic term, I would have to subtract it from both sides, and it's actually going to cancel on both sides. Okay. So we end up with a negative 1 equals 4 minus 4 secant of A. And I can go ahead and subtract the 4 from both sides to get, I'm going to start writing secant on the left-hand side. To get a negative 4 secant of A is equal to a negative 5 divided by a negative 4 both sides. And we end up with secant of A is equal to a positive 5 over 4. Now, because on my calculator I don't have secant, I'm going to write this in terms of cosine. We're going to get that cosine of A is the reciprocal of this quantity, so we're just going to have a 4 over 5. And now I can go in and I can calculate what angle A is going to be by simply doing A will be cosine inverse of 4 over 5. And now remember, this does return reference angle. So actually, let me be very specific about that and write that this is our A prime or A hat, whichever symbol you want to use. Okay, so cosine is positive. That gives us two options for the quadrants that we can pick. Cosine is positive in quadrant number 1 and in quadrant number 4. So in quadrant number 1, the angle A is simply going to be the same as the reference angle, which is cosine inverse of 4 over 5. And that is, what is that going to be? Let's see. Cosine inverse of 4, and then this is supposed to be in radians, so I'm going to have to, oh, that's actually already good, 4 over 5. I'm getting about 0.6435. That's in quadrant number 1. The other place where cosine is positive is in quadrant number 4. So to get the angle there, we would have to do 2 pi minus the reference angle. So that's a 2 pi minus this cosine inverse of 4 over 5. Let's see what that is going to give us. Okay, so 2 pi minus cosine inverse of 4 over 5. That's going to be approximately a 5.6397. And that's both of these are in radians. Okay, now let's go back to what is the allowed range for A. The allowed range for A is 0 to 6 pi. So that means that we have to consider the angles that are coterminal with these angles, 0.6435 and 5.6397, all the way up to three full cycles, right? Because 6 pi is 3 full cycles. So I'm going to consider the one that is coterminal to, sorry, I'm kind of trying to pick my words, but 0.6435 plus 2 pi, that would be one angle that is coterminal, and that would be in the second cycle. And then there would be a third angle, 0.6435 plus 4 pi. Okay, so that would be completing 2 full cycles. So let me actually write that down. Okay, so since A is in the range of 0 to 6 pi, okay, we have one of the angle being approximately 0.6435, but then we also have 2 pi plus that, and then we also have 4 pi plus that. Of course, we wouldn't go to the next cycle because then that would be 6 pi and that would be greater than the allowed range. Okay, so let's see what that gives us. Just so that I have a little bit more accurate answer, I'm going to use this cosine inverse of, cosine inverse of 4 over 5 plus 2 pi. That's going to give us a 6.9267 approximately. Okay, for 4 pi, we're going to have, let's see, 13.2099. And all of those would be from the one that is in quadrant number 1. Just that. For quadrant number 4, okay, for quadrant number 4, we would have to go and add, same thing, 2 pi and 4 pi. So the first one is this 5.6397 approximately. The next one is going to be 5.6397 plus a 2 pi. Okay, we'll see what that gives us in a second. And then the next one would be 5.6397 plus 4 pi. And we'll see what that gives us in a second. All right, so for A, okay, we have 5.63, in fact, sorry, let me keep it more exact. It's 2 pi minus cosine inverse of 4 over 5. So we got that. Okay, so plus 2 pi. That's an 11.9229. Next one, 18.2061. Okay. Those are all the ones that we get from the ones in quadrant 4. But even then, we're not done yet. I know. We're not done yet because this is for angle A, right? For angle A, A was representing, let's go back to the top, A was representing 3x. So now we have to write it back in terms of x. Okay, so 3x is equal to this A part, so 0.6435. That means that we're going to get x is approximately, divide both sides by 3, and we are going to get, let's see if I can bring back the original expression. That way we get the most precise answer. Okay, so it would be this cosine inverse of 4 over 5 divided by 3, and we get 0.2145. For the next one, we get 3x is equal to 6.9267. That gives us, let's see, again, I'm going to try to bring back the more precise answer. So the more precise answer being this cosine inverse of 4 over 5 plus 2 pi. In fact, let's just go ahead and type it again. Okay, so is that 6.9266 divided by 3? It's going to be approximately 2.3089. And for 3x being 13.2099, we're going to get x is approximately, let's see, 4.4033. Repeat the process here. I know this is very tedious work. Here we're going to get, this one was corresponding to the 2 pi minus cosine inverse of 4 over 5. So 2 pi minus cosine inverse of 4 over 5. We get this 5.6396 divided by 3. That's a 1.8799 approximately. Next one is this 11.9229 divided by 3. Okay, so let's see. So it's that plus 2 pi divided by 3, 3.9743. Next one. We get approximately 6.0687. Phew. Okay, so that's quite a bit of work, quite a few answers. I'm not going to go in and check them, but all of these turn out to be true solutions to the original equation. We can go in and check. Okay. So let's continue. We have only a few more examples. Example 6a is asking us to solve an equation that involves an inverse trig function. Okay, so just so that it looks a little more familiar, less intimidating, I'm going to write this as 2 times sine inverse of x is equal to pi. Divide both sides by 2 and we get sine inverse of x is equal to pi over 2. And so we know that sine inverse is returning some angle, right? So in fact, we know that if an equivalent form of writing that same equation, it would be to write x is equal to sine of pi over 2, because that's the angle that it returns. Okay. So what is sine of pi over 2? Well, that's just 1. In fact, let's go ahead and check. Is it true that 2 times sine inverse of 1 is equal to pi? Okay, well, let's check it out. 2 times sine inverse of 1 gives us 3.1459, and well, that's exactly pi. Okay, so, yep. Pi equals pi, which means that looks good. Nothing compared to 5D in terms of the work. Okay. Let's take a look at another one. In this equation, we actually have 2 sine inverses. 2 inverse functions. One of them is cosine, the other one is sine. Thankfully, though, there's for the sine inverse, this has a value. So what we can do here is to write the equivalent expression of this. If cosine inverse of x gives you this, which is supposed to return an angle. Okay, so just to make it easy on ourselves, let theta be that angle that is returned by sine inverse of 1/2. Then what we're solving is cosine inverse of x is equal to theta, and that is equivalent to x being cosine of theta. All right. Now we've solved this type of problem before. If that is my goal in my given, is that sine of theta is equal to 1/2 simply by rewriting this equation again with sine theta. Well, what I can do is I can, well, actually, hold on, let me pause there, because that's one given. The other given is that since sine inverse returns an angle between negative pi over 2 and pi over 2, that this angle will be in either quadrant 4 or quadrant 1. Since it's positive, we'll be drawing our diagram in quadrant 1. Okay, so opposite to angle theta is 1, hypotenuse is 2. I'll leave out the Pythagorean theorem work, but you can verify that this is going to be square root of 3. So if we're looking for cosine of theta, then we'll have that it's going to be adjacent, which is radical 3, over hypotenuse, which is 2. Now we can check. Is it true that cosine inverse of square root of 3 over 2 is going to be sine inverse of 1/2? Well, let's see. Okay, because it's that number and then sine inverse of 1/2. Same number. Okay, so looks good. Okay, and last equation. This last equation, we have arc sine of s minus arc cosine of x equals pi over 6. Okay, again, what you want to do in this case is solve for either one of the inverse functions. In fact, just so that it looks a little more familiar, I'll write it in this form. What I'll do is I'll solve for the sine inverse of x. And that'll be a pi over 6 plus a cosine inverse of x. Okay. And then what I'll do is, since I'll try to solve for x in this case by writing this as x is equal to sine of pi over 6 plus cosine inverse of x. Now, it doesn't seem like we've made much progress, but we actually have, because from here, well, first things first, since this is the result of taking sine inverse, it means that this angle here, this pi over 6 plus cosine inverse of x, has to be in the range of negative pi over 2 to pi over 2. And since it already looks pretty complicated, I'm going to let cosine inverse of x be theta. Okay, so let theta be the angle returned by cosine inverse of x. And then this whole thing simply becomes a new goal. The goal is to find x is equal to sine of pi over 6 plus theta, where pi over 6 plus theta is in the range negative pi over 2 to pi over 2. And so I guess that we could have listed as a given. Let me actually do that there. I'll just list it here. This is given. Okay, what else is given? Oh, okay, I'll leave it there. What else is given? Well, it's also given that if theta is equal to cosine inverse of x, it's also given that cosine theta is equal to x. That's one of them. And the other one is that cosine inverse is returning an angle, and it always returns an angle between 0 and pi. So theta has to be between 0 and pi. So that's another piece of given. So I'll just go ahead and list this one over here as well. Okay. So how can we work towards the goal? Well, this looks like sine of the sum of two angles. Pi over 6 plus theta, that's the sum of two angles. So as far as the work, I'm going to use one of the identities to help me out. Which I'll continue on a separate sheet. So sine of pi over 6 plus theta. The sum formula for sine tells me if I have sine of a plus b, that's going to be sine a cosine b plus cosine a sine b. So this will be sine of the first angle, which is pi over 6, times cosine of the second angle, which is theta, plus cosine of the first angle, which is pi over 6, times sine of the second angle, which is theta. Okay. Now sine of pi over 6, I have that on the unit circle. If you refer to the unit circle, sine of pi over 6 is 1/2. So we have 1/2 cosine theta. And then cosine pi over 6 is also on the unit circle. That's going to be a radical 3 over 2 times sine of theta. Now look at the given. It's given that cosine theta is x. So this here is x. Okay, so this becomes a 1/2 x plus radical 3 over 2 times sine theta. We can figure out what it is by drawing a diagram. Okay, so let me draw the diagram. I have enough space over here. The original sheet. Now determining the quadrant is going to be the tricky part because we did have two inverse functions with two inverse functions of non-numeric arguments. Okay, so we didn't have numbers here, we just simply had x. But from what we were able to figure out, those two told us that theta has to satisfy being between 0 and pi, and it also has to satisfy that when you add a pi over 6 to it, that it's between negative pi over 2 and pi over 2. So with this given, I'm going to work a little bit more. I'm just simply going to write this as pi over 6 plus theta has to be less than a pi over 2 and greater than or equal to a negative pi over 2. And then from there, we can subtract the pi over 6 from both sides. So this can become a negative pi over 2 minus pi over 6 is less than or equal to theta, which is less than or equal to pi over 2 minus pi over 6. Write this as a 3 pi over 6, and we get a negative 4 pi over 6 is less than or equal to theta is less than or equal to, again, write this as a 3 pi over 6, and you'll get a 2 pi over 6. Okay, then those reduce down to negative 2 pi over 3 and pi over 3. Okay, so we actually have two restrictions on where theta can be. Okay, this is the first condition. It has to be between 0 and pi. So it has to be somewhere in quadrant 1 or quadrant 2, because that's 0 to pi. But then this is the second condition. It also has to satisfy that it's between negative 2 pi over 3 to pi over 3. Now, you guys have seen this type of problem before. Okay, let me just rewrite it on a sticky note in a form that you've seen before. If I have an inequality that says that theta has to be between 0 and pi, okay, the way that I would graph that on the number line, if we're just talking about numbers, is let's say this is 0, this is pi over 3, this is 2 pi over 3, and this is pi. Then all of the numbers that satisfy this would live between 0 and pi. So they would live there. But we have a second condition, right? That was the first condition. The second condition is that theta has to also live between negative 2 pi over 3 and pi over 3. Okay, so again, on the number line, let me just draw the negative pi over 3. And then the negative 2 pi over 3. And then the negative pi. Okay, so drawing now the second inequality, I'll do that one in green. That one would be from negative 2 pi over 3 included up to pi over 3 included. That would be these numbers right here. So where is the overlap area? The overlap area is here. 0 to pi over 3. So both of these result in theta has to be between 0 and pi over 3. Okay, those two conditions boil down to one condition there, the overlap area. 0 to pi over 3, that's quadrant 1. So we're going to draw our diagram in quadrant 1. So theta is in quadrant 1. Okay. So let's draw the diagram, quadrant 1. Okay, what do we have for theta? We're given cosine. Okay, so cosine of theta is x, which we could express as x over 1, and that is going to be adjacent over hypotenuse. So that means the adjacent side is x, the hypotenuse is 1. If we do some Pythagorean theorem to try and find out what the opposite side is, we're going to get x squared plus b squared equals 1. B squared is equal to 1 minus x squared. And then b is equal to square root of 1 minus x squared. Notice I'm taking the positive root because we are going up in the positive y direction. Okay. So why are we doing all of this work? We're doing all of this work because we were trying to find sine of theta, which now we can, thanks to this diagram. Sine of theta is going to be opposite over hypotenuse, which is square root of 1 minus x squared over 1. So we're just simply going to end up with square root of 1 minus x squared. Okay, so let's put it all together now. Originally, the goal was to find x equals sine of pi over 6 plus theta. Well, sine of pi over 6 plus theta ended up being this expression. So this whole time, that's supposed to be x. So putting these two together, we get one equation. X is equal to 1/2 x plus square root of 3 over 2 times square root of 1 minus x squared. I'm going to subtract a 1/2 x from both sides of the equation. And that's going to give me a 1/2 x is equal to, here obviously it cancels because that's why we're subtracting in the first place. Square root of 3 over 2 times square root of 1 minus x squared. I'm going to multiply both sides by 2, that way I get rid of the 1/2s. These are going to cancel. We end up with x is equal to square root of 3 times square root of 1 minus x squared. To get rid of the squares, we're going to, to get rid of the square roots, I'm going to square both sides. So we'll end up with x squared is equal to square root of 3 squared would just be a 3 times 1 minus x squared. Then this becomes x squared is equal to 3 minus 3x squared. Add the 3x squared to both sides to get 4x squared is equal to 3. Divide both sides by 4. We'll continue over here. And you get x squared is equal to 3 over 4. So that finally we have x is plus or minus square root of 3 over 4. That's going to be x is plus or minus square root of 3 over square root of 4. But square root of 4 is just 2. Okay. Now notice, because we squared because we, sorry, not we started, because we drew this diagram, we already know that not both of the answers are going to be true solutions. X is supposed to be positive because it is on the positive x-axis. So we're only going to keep the positive answer. X is equal to radical 3 over 2. All right, so that is the answer to this final problem. We can go ahead and check. Is it true that sine inverse of radical 3 over 2 minus cosine inverse of radical 3 over 2 is equal to pi over 6? Well, let's check it out. Sine inverse of square root of 3 over 2 minus cosine inverse of radical 3 over 2 is this 0.5235. Let's check what pi over 6 is. Same number, thankfully. Okay, cool. Thank you so much, guys, for being here for this pre-recorded lecture. Hope to see you guys on Monday. And remember, I do have office hours Thursdays, 2 to 3 p.m. So if you have any questions, please feel free to join office hours. Okay. All right, guys, take care.